Picture the early days of computing. You had massive, room-sized machines, but they were strictly bottlenecked by their programming. You could load up exactly one job at a time, hit run, and wait. These were what we call single-process systems. The hardware itself simply didn't have the logic required to juggle multiple tasks. You were either running a program or you weren't doing anything at all. This created a severe structural flaw. From the second that program started executing, it held the entire machine hostage. The computer was locked into that single operation, completely unresponsive, until the job naturally finished, or until it crashed. The hardware was completely submissive to the software. If a program had a flaw or hit an infinite loop, you couldn't switch to another app or cancel the command. You were essentially working with an incredibly expensive, highly fragile calculator. Imagine taking that exact same rulebook and trying to run a modern device with it. Think about what happens if you open a heavy, demanding application, like a social media feed, on a phone that lacks a central manager. This pie chart illustrates the available processing power and memory on your device. Without rules, a single greedy application will immediately engage in resource hijacking. It will aggressively expand to claim 100% of that CPU and RAM for itself. Because the first app took everything, any other program you try to open hits a brick wall. We call this process starvation. That second app is completely frozen out because there are zero physical resources left to load its code. To fix this on their own, app developers would have to write custom instructions to manage the hard drive, the memory, and the processor themselves. Writing that repetitive code for every single app drastically slows down software creation. A digital environment lacking a central authority cannot sustain multiple programs. It inevitably collapses under the unregulated resource demands of its own applications. To prevent this total systemic collapse, we introduced an enforcer. The operating system was designed specifically to sit in the middle of this chaos and regulate how hardware is distributed. Look at this structural diagram mapping the user's apps at the top down to the physical hardware at the bottom. Think of the hardware as a bank vault. Applications are no longer allowed to walk directly into the vault to take what they want. They have to submit a request to the operating system, which acts as the teller. This dynamic creates something called abstraction. The operating system hides all the messy physical mechanics of the hardware. A developer can simply ask for 10 megabytes of memory, and the OS handles the complex routing to find free space on the physical disk. Because programmers no longer have to reinvent how to talk to a physical processor every time they write code, they can focus entirely on the user experience. Abstraction cleared the path for the rapid explosion of modern software. But letting multiple programs run side by side introduces a new risk. If a video game and a spreadsheet are sitting in the same physical memory, a stray line of code from the game could accidentally overwrite your financial data. To solve this, the OS maps out the physical RAM, shown in this grid, and enforces strict memory isolation. It assigns entirely distinct, heavily walled-off blocks of memory to each active program. Neither application knows the other one exists. A demanding app cannot peer into, siphon resources from, or corrupt the memory space belonging to a background task. This architecture acts as a digital quarantine. If one specific application encounters a fatal error and crashes, the damage is contained exclusively to its assigned block. The rest of your system survives intact and keeps running. Controlling the memory is only half the battle. The operating system also has to manage time. For that, it relies on a module called the scheduler, a ruthless arbiter that dictates exactly which app gets the processor's attention. As you can see in this timeline, the scheduler uses a technique called preemptive multitasking. It forcefully pauses a greedy application and chops up the processor's availability, dealing out tiny fractional slivers of CPU time to all your active programs in rotation. At the exact moment two blocks intersect, the system performs a context switch. It instantly saves the precise state of the paused application, archives it, and loads the data for the next one into the processor. Because the OS can swap out instructions on demand, it isn't locked into a single process. It can immediately drop a routine background task the second a high-priority emergency job requires attention. For example, the instant you plug in an external piece of hardware, like a USB drive, the hardware sends a trigger. The OS interrupts whatever it was doing and forces an immediate antivirus scan to check the new drive. When you have a single processor, True simultaneous multitasking is actually an illusion. What you are experiencing is a highly disciplined, hyper-fast rotation of individual tasks, executed and swapped in mere milliseconds. We've moved far beyond those early, fragile machines that could only process one rigid command at a time. Today, we expect a completely fluid digital environment where dozens of tasks run side by side without colliding. This is entirely due to the operating system. It eliminated process starvation, enforced strict digital boundaries, and tamed software's natural greed. By providing a reliable layer of abstraction, it continuously empowers creators to build increasingly complex tools. Programmers don't have to worry about the metal inside the machine, they just write the logic. It sits out of sight, acting as a strict but fair manager. The operating system takes a chaotic tangle of raw electrical signals and transforms it into the stable digital reality we interact with every single day.